Hello guys, welcome back to another video. In this lesson, we are going to cover an introduction to the gas laws. Let's first start to talking about the things that we can modify to affect the behavior of gases. So things that we can control are temperature, pressure, volume, and the number of moles. Depending on how each of these variables is manipulated, we will see the behavior of gases vary. Now, in order for us to determine how each of these individual variables affects the behavior of gases, we are going to manipulate two of them, and then the other two will have to stay constant. So we're going to look at a different combination of these variables in just a moment. So let's start with a quick recap about when we talk about moles, because it's been a while since we last talked about them. We have Avogadros number, 6.02 times 10 to the 23rd, and that is particles of an individual mole. And don't forget, the moles refers to the number of gas molecules within that mole. When we talk about volume, we're talking about the amount of space that is occupied by a gas. And also, for the purposes of our calculations that we will learn later on, we will have to use volume measured in liters. So let's go ahead and start talking about the first gas law, and that will be Charles. I like to start with this one because that's the one that we can mostly see. So, for example, Charles' law states that as temperature increases, the particles would have more kinetic energy, and therefore they're going to be able to travel further out, right? So the distance that they cover is going to increase. They have more energy in them because the temperature went up. Now, think about that. Well, the area that they occupy is going to be much, much larger. So therefore, we can determine that Charles' law is going to have a direct relationship. If the temperature increases, then the volume increases. If the temperature decreases, then the volume that the gas particles are taking up is also going to decrease. So we have an equation that we will not use just yet, but we will have later lessons into each individual gas law, and we're going to learn how to use the calculations. But for right now, we just need to know that this is the equation that we use for it. There's a different way that we can modify it, and I like the other way better. But for right now, we're going to have this one. Now, of course, because we're talking about temperature and volume being modified, then we know that we can only use two of the constants at a time. Two of the variables at a time, so the other two have to stay constant. So in Charles' law, what is remaining the same is the pressure and the number of moles. So here we have a visual of Charles' law. And we saw a very similar simulation of this where assuming that we have the same amount of particles, right, the number of moles stays constant, and assuming that we are going to continue with the same pressure, if we were to decrease the volume that all of these particles are in, then, if we were going to increase the volume of these particles, and yet we want the pressure to remain the same, then that means that they're going to have to hit the walls of the container more often. And therefore, in order to preserve that pressure, and without adding any more particles, then the temperature of them has to increase. So therefore, it has to start moving faster so that they can hit the walls of the container more often to increase the pressure, right, to maintain it the same. So an increase in the volume would also represent an increase in the temperature. So that was Charles' law. Let's move on to the next one. Up next, we have Boyles Law. Now, Boyles Law is going to be an inverse relationship because what we talk about here is, let's say that we start with the high pressure and a really low volume. So remember, pressure is the force that the particles hit the walls of that container, right? So they're hitting the walls because they're moving fast, they have a random motion, so over time they're going to collide with the container, right? So if the container is really small, the volume is really, really small, then they're going to be hitting the container more often, and therefore the pressure goes up. But what if we start to increase the volume so the container gets larger and larger and larger and larger? Well, think about the particles themselves. They're going to have to start traveling further out to hit the container, right? The walls of the container. And also, because you're adding the space between them, they're using up that energy, right? So the pressure is going to go down over time. So as the volume goes up, the pressure decreases, and vice versa. We have our equation here on screen, which we will not do any calculations just yet. But for the constants, if we're modifying pressure and volume, then our constant is going to be the number of moles and the temperature. So here we are assuming under Boyles' law that we did not add or remove any number of particles and that their average kinetic energy remain the same. So they're not moving faster, they're not moving slower, they're moving with the same amount of kinetic energy. So an example of that would be what we have here. Let's say that, again, we have the same number of moles, so same number of particles with the same amount of energy, each of them. So the volume gets smaller and smaller and smaller. So what's going to happen is that because the area where the particles are moving is going to be reduced, then they're going to be hitting the walls of the container more often. They're not doing so with much force because we haven't given them any more kinetic energy, but they are going to be hitting the walls more often, and therefore the pressure is going to increase. So as the volume in this scenario went down, the pressure went up. Let's move on to the next one, Gay-Lussac's law. This one is also a direct relationship. And this one makes a lot of sense if you really think about particles as like just the movement, right? The things that are moving, particles having that random motion. So for this one, as we increase the temperature, so we're giving the particles, right? Because temperature is average kinetic energy. If we give the particles more energy, more and more kinetic energy, that's movement, right? They're moving faster and faster and faster and faster. Well, if pressure is, the definition for it is the amount of force and the collisions that the particles have with the container, well, if they're moving more often, they're moving faster, right? They're colliding, they're crashing, they're hitting the walls of that container more often. So therefore, the pressure is going to go up. So of course, this is assuming that the number of moles is staying the same and the volume did not change. So we're not adding a container that is larger or smaller. The container stayed the same. We give the particles more energy, they move faster, and because they move faster, they have more energy in them, so their force that they're hitting the walls of the container is going to be more often with much more strength. So pressure goes up. So what I have here for the visual is a flask with an ice bath and boiling water. Same amount of particles, but look at the very top where we have the atmospheres. Where the particles are in the ice bath, they don't have as much kinetic energy, right? Some of that is going to actually be transferred towards the ice cubes. But on the other scenario, we have water that is boiling. So that water is transferring some of that energy into those particles. So the temperature of those particles, so the average kinetic energy of them is going to be much higher. So therefore, moving faster, hitting the walls of the container more often, and therefore the pressure goes up. Last one is going to be Avogadros. And we're very familiar with Avogadro because we've been doing a lot of calculations with Avogadro's number. But there's also Avogadros Law, which of course is going to involve the number of moles. Now, Avogadros Law is also a direct relationship. Note how all of them were direct relationships except one. So it's important. That's an easy way to remember what kind of relationship they have. Just remember the one that is inverse, which was Boyles. So what we have here is going to be the number of moles. Now, obviously, if we keep the temperature and we keep the pressure constant, so we're not giving them more energy, they're not hitting the walls of the container more often, or less often for that matter, that's staying the same. So let's think about what's going to happen. The more moles you have, right, the more particles that are in the container, the higher the volume is going to be, right? Because if we don't want the pressure to increase, meaning all these particles that we're adding into the container, they can't hit the walls more often because pressure staying constant, that's not changing. Then that means that in order to make up that difference, the volume of the container has to be larger. So the more moles there is, the higher the volume has to be in order to keep the temperature and the pressure the same. Here again, we have our equation. Again, we're not doing anything with the equations just yet. There will be video lessons for that later on. But that's Avogadros Law. So what I have here is, again, a visual. So in the first, on the left, we have 6 particles, and they're taking up some volume, right? Smaller volume. But the moment that we add more particles, it's going to be required to have a higher volume because we don't want the pressure to increase. So we have to give them more space, right? Because there's more particles in the first place. So that's pretty much it, right? Those are 4 gas laws that we're going to look at for right now. We are going to learn later on about the combined gas law and also the ideal gas law, but those will be later lessons. Right now, we just need to understand the relationship between the variables, which ones stay constant, what are the names of the laws, and what kind of relationship do they have, direct or inverse. Now, I want you to start thinking about this particular question. We are not going to answer it in this video. That will be a different lesson. But think about this. Looking at the 3 equations we learned, which actually there were 4 because we talked about Avogadros as well. But let's just talk about Charles, Boyles, and Gay-Lussac's. About the 3 equations that we learned, is there any way to combine them into a single equation? So again, there wasn't just 3, we learned 4. But think about these 3 main ones. And I want you to start thinking, how can we combine them all to do a combined gas law? And we will answer that question in a different lesson. Other than that, guys, thank you so much for watching.